Torque is a wonderful concept that we all love to work with. It's force combined with leverage, okay? So here, I think the best way to describe it is with a wrench and a bolt. And here is the axis of rotation straight down through the center of the bolt there. And we want to make that bolt rotate. Well, a certain amount of torque is going to be required to do that. So how do we produce torque? We need to apply a force that is perpendicular to the lever arm. This is the lever arm right here, this long part. And it's the distance between the axis of rotation and where that force is applied. So in this case, if we wanted to apply torque on this thing, it would be that distance, which we would call D, which is the length of the lever arm. All right? And in order to find the torque that we apply, we say T equals the perpendicular force times the length of the lever arm. Now, if this torque is, or this bolt is really in there and we're not able to produce enough torque to make it turn, meaning we can't apply enough force, then we have a couple different options of how we can do that, or how we can make it turn. The best option, especially if we're just not strong enough, is to go get someone who's really strong. If there's no one around, then you can extend the length of the lever arm. You get yourself a longer wrench, all right? Because if you're only able to apply a certain amount of force, the only way you can increase the torque is by increasing the length of the lever arm, the distance. You get more leverage. If you apply this same force out here at the end of the wrench, then you're going to produce double the torque that you would if you applied that force there, assuming that these distances are equal. Okay, so applying more torque means that you're either applying more force or you're having more leverage. Okay, and we often talk about this in terms of the seesaw problems. I'm sure you remember. We put some hefty person on the seesaw there, and we have a slight person on the seesaw there. This is a wonderful drawing. And we all, the questions that we've been asking were, how far away would this person need to sit in order to make this seesaw balance? Or we could also ask whose side would be on the ground if this person was a certain distance away and that person were a different distance away. We want to remember that the axis of rotation is right there at the tip of the fulcrum, and that's the point where this seesaw will be rotating around. So if we want to determine what the torque in the counterclockwise direction, that's this way, is going to be, we take that force in the perpendicular direction, straight down, and we multiply it times the length of the lever arm. How far away are they? That's D. All right? And we can do the same thing for the other person, the torque in the clockwise direction. That's this way. We want to know what their force is. I keep writing force instead of torque, vice versa. And here's D in that direction. So how far out will they need to sit in order to balance this person? Okay, in order for these people to be balanced, the counterclockwise torque has to equal the clockwise torque. These two things have to be equal and opposite in order for the two people on the seesaw to balance. All right, well, let's put in some more information. Let's say that the big boy here has a mass of 80 kilograms. All right, and we'll say that the little person has a mass of 40 kilograms. All right, so how do we get from the mass into the force perpendicular? Well, if someone has a mass of 80 kilograms, how do you figure out what they weigh? Because their weight is actually that perpendicular force. And you know that if you have a mass of 80 kilograms here on Earth, where gravity is 10 meters per second squared, you have a weight of 800 newtons. Likewise, this person over here would have a weight of 400 newtons. That weight is, in this case, the perpendicular force, because that's what you're pushing down with on this seesaw. All right? Let's say also that this person is 2 meters away from the axis of rotation. Well, then how far away would that person need to be would be typically the question that we're asking. So if this person is 2 meters away, the big person's 2 meters away, then we would multiply 800, their weight, times 2 meters, to get the total counterclockwise torque, and that would be 1,600 Newton meters. That's how that's our unit for torque, Newton meters. All right. Now we take this information, knowing that it's 1,600 Newton meters of torque being produced on this side in the counterclockwise direction. That means that there must be 1,600 Newton meters of torque produced in the opposite direction in order to have this thing balanced. So we say 1,600 Newton meters equals 400 times whatever distance this guy needs to sit away from the axis of rotation of the fulcrum. So in this case, we're going to divide 1,600 Newton meters by 400 newtons, and that's going to equal D, which is going to be 4 meters. All right, and that's how far this skinny person would need to sit, because their weight is 1/2 of what the hefty person's weight is. All right, seesaw, balanced torques, that's what that is.